Hey team, I'm Maddie. Welcome to Science Side Up, and today we're talking about the ideal gas law. The ideal gas law tells us how pressure, density, and temperature relate to each other for an ideal gas. Now, what is an ideal gas? Great question. An ideal gas has three properties. One, there's no forces that are acting on the molecules in our gas that's going to cause them to either attract or repel each other. The second assumption is that there's no chemistry going on. No chemical reactions are occurring that would complicate our gas or something like that. We just have these molecules and they're not really interacting with each other. And our third assumption is that if two of our gas particles collide either with each other or say they bounce off a wall, then we assume that that collision is a purely elastic collision. An elastic collision is one in which no energy is lost from the system. A great way to think about that is if you have a gas particle that collides with a wall in a purely elastic collision, then the speed at which the gas particle hits the wall will be the same speed at which it bounces off the wall, and the wall doesn't move or gain energy or do anything interesting. If you can think back to your high school chemistry, or if you have taken high school chemistry, you've probably seen the ideal gas law written as PV equals nRT. P here is pressure, V is volume, N represents the number of atoms that you have of your gas. You can also just think of it as mass. R is our gas constant, and T is temperature. For atmospheric stuff, we usually write this equation in terms of density instead of volume and N. So pressure equals rho RT, pressure, density, gas constant, and temperature. So the gas constant is a constant for an ideal gas, but obviously no ideal gas actually exists in real life. So for any given gas, the gas constant for that thing can be experimentally determined. Let's think about a couple applications of this law. Please imagine with me some cylinder container with a plunger so you can change the amount of volume that the gas can occupy, like a bike pump. Now, if we were to pump our bike pump or move this plunger in, our new scenario is going to look something like this. So we've clearly increased the density of our gas. So temperature and pressure are going to follow from this change of density because our gas constant is, by definition, constant. So let's say that we hold pressure constant inside our container. We're able to do this by the magic of science thought experiments, okay? So if we hold our pressure constant, then the temperature in this container will have to drop in order for this equation to stay balanced. Similarly, if we hold temperature constant but allow pressure to change, if the density goes up, we'd have to also see pressure increase. A great example for this relationship is like a CO2 canister for a paintball gun, or even one of those canned air spray thingies you use to clean your keyboard. When you either fire your paintball gun or press down to use that gas, what comes out is really cold. What's happening there is that the pressure is suddenly dropping and the temperature drops to follow it. So when you're releasing the gas from that compressed state, pressure suddenly falls off and you feel that as cold on your skin. Okay team, that's all I've got for you today. I hope you liked this video and I will see you all in the next one. Bye team! So yes, this is a re-uploaded video, my first attempt at an ideal gas law video. I misspoke a couple times, and the example that I gave of the paintball gun, I don't know what I said, but the comment section let me know that it definitely was not read as, I didn't explain it well. So I want this to be a good resource video, and I hope this is better. Thanks for sticking around, team.